So let's talk about the ways that we can make alcohols. First, there are substitution reactions. The leaving group is replaced by the hydroxy group. This works with a primary substrate. We use an SN2 reaction with a strong nucleophile. This would be something like sodium hydroxide. It works with a tertiary substrate, here with a weak nucleophile, something like water or ethanol. We'll add these hydroxy groups. Now, the substitution reactions are not going to work well for secondary substrates because they're going to be in competition with elimination reactions. So let's look at the other way. Let's look at addition reactions. We can use dilute acid for acid-catalyzed hydration. This works well. It forms a carbocation intermediate, and sometimes we get carbocation rearrangement with an acid-catalyzed hydration. We can avoid that complication by using the mercury compounds here, the oxymercuration, demercuration process. Both of these processes will add the hydroxy to the more substituted carbon. If we want to add it to the less substituted carbon, we do the hydroboration oxidation reaction. We can also prepare alcohols via reduction. Now we're going to take a little side trip off to oxidation states. I know you had this probably in 170 and in 180, but we're going to talk about it again just a little bit here. When we assign oxidation states, we treat all the bonds as ionic and give all the electrons to the more electronegative atom. If the atoms are the same, then the electrons are split. Okay, so if we have this methanol, what we're going to do is we're going to give all of the electrons that are shared between the hydrogen and the carbon are going to go and live on the carbon for accounting purposes only. This is not where the electrons really are, but it's more of an accounting issue. Between the carbon and the oxygen, these electrons are going to go and live solely on the oxygen. So when we look at the number of carbons around the number of electrons around our carbon, we see that we've got 6 electrons. Well, we know that carbon would like to have 4 electrons, but it's got 6, so it's got 2 extra ones. So we assign the oxidation number of -2. because we have 2 extra electrons. Down here we've got the oxidation states for a bunch of different carbon compounds. So we can look at, say, methane. In methane, carbon is going to keep all of the electrons because it's more electronegative than the hydrogen, and we end up with a carbon that has 8 electrons. Carbon would like to only have 4 electrons, that's its normal, and so we get an oxidation number of -4. Then let's look at the other extreme. Let's look at carbon dioxide. We have carbon dioxide, all the electrons go to the oxygens, and so we get a carbon that has 0 electrons. And so carbon dioxide gives an oxidation number of +4. It would like to have 4 electrons, but it doesn't have any. You'll recall that oxidation means loss of electrons. You can also see it as an increase in oxygen or a decrease in hydrogen when you're looking at your formulas. You can see that if you increase oxygen, you're going to be removing electrons, and so you're losing electrons. If you decrease hydrogen, then you are adding electrons because those electrons go to the carbon. So oxidation is going to increase your oxidation state. Reduction is the gain of electrons, and it causes a decrease in the oxidation state. So if you have methanol and it's converted to formaldehyde, so we're up here at methanol, and we convert it to formaldehyde, we're going from -2 to 0. The methanol is oxidized because we've increased oxidation state. If we go from methanol to methane, we go to methanol to methane, we're going from -2 to -4, and the methanol has been reduced. A quick way to remember this is that oil rig. Oxidation is loss, reduction is gain. And this is of electrons. So, has this compound been oxidized or reduced or neither? So first we look at the reactant, and we see that we've got a carbon and a carbon, and those electrons get split. One goes to each carbon, and also that occurs over here as well. So the carbon of interest has 2 electrons. The other electrons all go with the oxygen because it's more electronegative. If we look at the product, we see that, again, the oxygens have taken all of the electrons that are between the oxygen and the carbon, and the oxygens between the the electrons between the carbon-carbon bonds are split. So again, we have 2 electrons, so neither is the answer here. Nothing has been oxidized or reduced. Now this is a term I always avoid in 140 because I think it's confusing. Reducing agents. We really can't get away from it for y'all. Sorry. Reducing agents are oxidized. They are agents of reduction, so they cause something else to be reduced. Cause something else to be oxidized. That's why I avoid it. The reducing agent is oxidized, and so because it's causing another compound to be reduced. So hydrogenation in the presence of a metal catalyst is our first example. This one is rarely used, partly because of the high temperature and pressure, and partly because if the compound of interest has a double bond or has anything else of interest, it wipes it all out. But it does cause reduction. Sodium borohydride is used to reduce ketones and aldehydes. Sodium borohydride functions as a source of hydride. And remember that this has electrons with it. That's a hydride. This is a proton, and it's a hydrogen without its electrons. The hydride by itself is not a good nucleophile, but it tends to work as a base. We don't want a base here. We want a nucleophile. The mechanism is to transfer the hydride, and I've got it written down below. We're going to transfer the hydride. Again, we're transferring these electrons are getting transferred and adding this hydride right there. And then we have a proton transfer. Now the proton transfer step, the water step, has to be done separately because of the water would react with the sodium borohydride. The product will be racemic if a chiral center is produced because the hydride nucleophile can attack either face of the planar carbonyl group. This is a plane. And so it can attack the front or it can attack the back, and so you get both enantiomers. Another option for reduction is lithium aluminum hydride. This is a structure very similar to the sodium borohydride, and it's going to deliver the hydride here. It's a two-step mechanism, and it reacts violently with water. So this second step has to be done separately. The mechanics for our purposes is going to be pretty much the same as the sodium borohydride. If a chiral center is produced, you produce a pair of stereoisomers. Now, both sodium borohydride and the LAH will reduce ketones and aldehydes to alcohols, but they do not affect double bonds. So they work better. Okay, the LAH will react with carboxylic acids and esters to produce alcohols as well. Sodium borohydride does not. So that's a difference if you're depending on your synthesis as to which one of these compounds you might pick. I think that diagram is down here. We have a carboxylic acid. We can add our LAH and make our alcohol. If we have an ester, if we have excess LAH, we can make two alcohols. And what happens is that it reacts twice because we've got our two oxygens. If you want to look up the mechanism, it's in your textbook. There are many different forms of sodium borohydride and LAH available, and they replace the hydrogens with different R groups, and that modifies the selectivity and reactivity of the hydride agent. So if you're in the business of using these compounds, there are a number to choose from, not just the plain vanilla. Okay, so let's draw the mechanism and predict the product. We start with this compound. The electrons that are here between the aluminum and the hydrogen are going to attack that carbon right there, and these electrons are going to go up and live temporarily anyway on the oxygen, and that will produce an oxygen up here that's got a negative charge. It will produce the hydrogen is added to that carbon, and we've got a CH3 group here. All right, then we'll just have a plain proton transfer. I'm going to change my color again. The electrons from this oxygen are going to attack that proton this time, and these electrons will go live on the oxygen, and that will leave us with, I guess I'm going to do the colors, purple, hydrogen there, we'll have CH3 there, and our pink hydrogen in the front. Plus the enantiomer. Don't let me forget the enantiomer. Okay, next we'll be looking at diols.